Right. Okay. Okay. And I hope everyone is happy with the recording. Let's start. So basically, we are in the middle of discussing a Bayesian network, and we did discuss what's a Bayesian network and how it's used for deducing some inference on the world, representing the knowledge on the world and deducing some inference. We also discussed the context of Bayesian statistics and how you update your belief about the world, the subjective view of probability about the world. And we discussed the concept of conjugate priors. Now we started to discuss conditional independence and how you can read conditional independence from the network. And today I want to show you an example of another example of how these things happen. That type of thinking will help us in our search for ways to construct the Bayesian network automatically or semi-automatically from the data. So you can see here that I have this simple Bayesian network with variables A, B, C, D, and E. And what I want to ask myself is, what I want to make the observation is that if I know A, then conditioned on A, C and B and D are independent. Okay, that's what I want to notice. So you can think about B and D. Why I'm choosing B and D? B and D are like they're not descendants of C. Okay, so once I know A, the non-descendants of C are conditionally independent with C, and this is just an example of this principle, and I want us to see how we can see that formally. Okay, and it will remind us of how we reason about the Bayesian network. So let's look at it. So I'm starting from the probability of C given A, B, and D, and I want to show that that equals to the probability of C given A, which is here, and that will show that the conditional independence, basically. Okay, because I can ignore B and D. Once I know A, I can ignore B and D. So I'm going to get this this statement that assuming A, C is conditionally independent of B and D. So what is the probability of C given A, B, and D? So just this is the probability of A, B, and D happening, and then assuming that the probability of A, B, and D happens. So the probability of C, A, B, and D, the joint probability, is the probability that A, B, and D happens, and then given A, B, and D, the probability that C happens. So this is what I wrote here, basically, right? If you take B, probability of A, B, and D, and you move it to the other side, that's what you have here. That's what is written. Okay, question on this stage? Or is it clear to everyone?
Looks clear for now.
Okay, great. Okay, so now I'm going to factor the two joint probability. One is A, C, B, and D, and the other is A, B, D. But I'm going to use my information about the neural network, about the Bayesian, sorry, the Bayesian network. So remember that from the Bayesian network perspective, once we factor the joint probability, whenever I have something like, say, C dependent on something, then it's going to be dependent only on its parents, not anything else. Or E will be only dependent on C and D when in the factorization. So when you factor the joint probabilities, you use the structure of the network to essentially simplify the factoring. So let's start with A, B, and D. So this is probability of A happening, probability of B happening, and probability of D happening assuming B. Now really I should have written something like probability of A happening and then probability of B happening assuming A. But B doesn't have a parent, so it simplifies to probability of B. And then I should have written probability of D happening, assuming B and A. But D has only B as a parent, so I'm left with probability of D assuming B. Same thing here at the top for probability A, C, B, and D. If you're not clear about this, try at home to factor probability of A, C, B, and D according to the laws of probability, and then use the Bayesian structure to simplify and see that you get to what I got here. Any question up to now? Is it clear?
Makes sense so far. Makes
Okay,
sense.
great. Now, you see A probability of A, probability of A, we can strike them out. B and B. D assuming B, D assuming B, we strike them out. And we're left with probability of C assuming A. So you see that assuming that A happened, B and D are independent of C. Okay? So we see first, we see a general way of reading conditional independence from the network. That is, if I know essentially if I know the parents of a probability of a variable, then the probability of that variable is independent of its non-descendants. So I know A, then C, the probability of C is independent of B and D. Okay, questions or comments about that? So I have a question. Assuming I'm conducting some sort of calculation about probabilities in the network, how is that helping me from a complexity point of view?
Because I think I understand what you're asking. If variables are independent, you don't have to like connect them in the graph, and therefore you don't have to model their like their relationship. Something like
Right. So essentially each node here, like the node C.
or you don't have to do the conditionals and stuff for them
Yeah,
because
right,
they're all it
right,
factorizes.
right. So essentially, like you should, when you think about the network, think about associating um, a distribution with with a set of distributions, with they call it tables sometimes, with each node. Okay, so for instance, in the node C, or let's think about A, B, C, and D and E as binary variables for a second. It will just simplify the description. There's nothing special about it. Everything I say now is applicable to any variables, okay? Including continuous variables, but you need to understand the principle first. So let me talk about A, B, C, D, and E being binary variables, they have two values. Then how many probability? So here for A, I would have two possible values, and I need just one number, one probability to model A, right? So the table associated with A is just one. It has one entry, right? The probability of A being getting a certain value, and then I know the probability of A not getting that value because there's just two values. Same thing with B. Now with C, so A can have two values, and for each of them, C will have a different probability function of its two values. So condition on A, I would have a table of two entries. Each one of them has enough to have one number. So say A can take values 1 or 0. So for A getting a value of 1, I have a probability for C getting a value of 1, assuming A got a value of 1. For A getting a value of 0, I have a probability of C getting a value of 1, which is again one number. So here for C, I need two numbers. How many numbers I need for E? How many rows I will have in the table representing E?
Rows or columns?
Rows.
It's like 4 on 2
Yeah,
matrix.
exactly. But because it's a binary, I just need one of the two columns, okay?
Yeah, the complementary.
Yes, yes. Exactly. So you're right. There's four rows. So for instance, for C getting the value of 1 and D getting the value of 1, E will get some probability for E getting the value of 1, and so on. So I have 4 rows. Now, think about, so now we're getting to, so you're right, George, exactly. And now we're getting to Sam's comment. So if you think about the probability of C given A, B, and D being equal to the probability of C given A, so if I need to represent the probability of C given A, B, and D, So A, B, and D in our example, how many rows would I have in the table?
8.
8. Now, because of the conditional probability, how many rows will I have in the table, actually?
2.
2. And that's exactly what Sam was saying. That's the answer, okay? So it's very important to understand conditional independence because it has a huge impact on complexity of different things you're trying to do. Both in terms of space, what we've seen just now in the example, but also in terms of runtime. We'll get to that. Okay, any other questions or comments at this point? Okay, so thank you very much for joining today, and we'll continue next time.
Thank you.
Thanks, Eitan. Appreciate it.
Thank you. Bye-bye. Bye.